Assalamu alaikum. So today is my second visit at NCP National Center of Physics. It's basically a 13th summer school at LHC Physics. So stay tuned with me. I'll update you each and everything.
Talk about him. So all the idea was simple that all the forces should unify in a single force at high energy, and one should find a framework, a mathematical framework which can unify these forces. And in this effort, when people were doing it, then the periodic table of the particle physics came into this. So before there was periodic. Missing of detection, we reconstruct them as what we call missing energy. So we sum up the energy of all non-particles that we are detecting, and then in the transverse direction, we think that they should spread up because the momentum should be conserved. Initially, there was no momentum in the transverse direction, so they should invariant mass of the pi zero, which decays to photon, the invariant mass of jet time for low momentum. So these two we can use to calibrate the energy scale or momentum scale at low energy. These we can use to calibrate the energy scale or momentum scale at high energy. And once you have well calibrated by using these mass peaks, then your data in Monte Carlo will agree very well. And then you can go and search for new things, because now you trust your detector that it is well calibrated. So what we are doing, we are at NCP, just introduce a little bit. It's not just the detector physics or the analysis of the data, it's about the computing, it's about the programming, it's about the statistical analysis. For that reason, I have also started these lectures on statistics a few years ago. So every year we invite one expert to give a series of lectures, like a course on statistical and high energy physics. So this year also, some of you, if you know Jonas, he is very expert in the area, and he will be here and coming back, and he will be giving series of lectures on how to interpret these observations. For example, how to claim the discovery, how to set limit on something if you are not able to claim a discovery. For example, if the signal is not visible, then what you would do, you will set limits. So how you are going to do it? So you need to learn the statistical concept, and you need to learn the tool, and you need to learn how to use them to interpret the data and the observation. On this FMP radio, 93.4, and that FM radio is basically it's the recitation of the Holy Quran, and then there is the Tarjuma translation in Urdu. And just the guy was saying that there are many things that I heard something which I didn't pay much attention to it before, and they were just saying that there will be a day when the what is called जैसे कहते हैं ना, जानवर जब जमा होते हैं उसकी काल उतारते हैं, ठीक है? तो जब काल उतारो तो आपको गोश्त नजर आएगा, तो कह रहे हैं I'm just speaking on Urdu because it will be hard for me to translate it in Urdu. So it says कि वो दिन होगा जब सूरज जो है बेनूर होगा और ये होगा। एक बार मुझे थोड़ा सा लगी कि वो फरमाते हैं कि वो दिन होगा जब आसमान की खाल उतारी, आसमान की खाल उतारी जाएगी, ठीक है? जब उतारी जाएगी तो आपको नजर आ जाएगा। तो I was just thinking like, okay, it might be somewhere, but there is a layer which is making it invisible. And To quote another thing on Nasr Fateh Khan की वो कवाली है कि वो में गोरख गंदा वो कहता है कि ये हर चीज करके फिर भी पोशीदा होती है. So it could be it's just somewhere here or maybe somewhere in the surroundings, but we don't see. Maybe the reason is we see things अगर लाइट उनसे इंटरेक्ट करे क्योंकि हमारे आंखों में या हमारे पास कोई ऑब्जर्वेशन हो, that matter is also something which we know exists. It doesn't mean it exists just here in the solar system, but it could exist in the galaxy where we are. But it somehow arrives to interact with us, somehow arrives to interact with the system, with our observations. And we have to find out, we have to be smart enough to come up with the idea to interpret it, to observe it. Okay? At least अगर हमें ये पता है कि डार्क मैटर या ये चीज़ें ये ऑब्जर्वेशन हमने किए कि ये एग्जिस्ट करती है, तो हमें एक ना एक दिन पता चल जाएगा कि उनके साथ इंटरेक्ट कैसे करें. So this is a struggle which should continue.
To describe the evolution of the universe. So let me start from the very basic. We all know about the gravitational law by Newton. So Newton actually tried to understand the fall of the apple, and he saw that this fall is very similar to the fall of moon towards the earth. And in this universe, we talk about this megaparsec. Megaparsec is 3 million light years, which is a typical intergalactic distance, the distance between galaxies. And the size of our Milky Way galaxy is about 30 kiloparsec. So in cosmology, we treat the galaxies like a point particle. Just like in high energy physics, you treat, let's say, electron as a point particle. So we are talking are treated as a point particle. So let me start from the Newtonian point of view of universe. So how Newton thought, the universe would have formed or have existed. So universe is infinite in space and time. So according to Newton, the universe was infinite in space and time and filled with stars, so uniform distribution of stars or galaxies, whatever. So you can see this distribution. And according to Newton, space is static. So space does not depend on the relative motion or anything else inside the space. So space is static. So this system, there is nothing which can stop these stars falling into each other due to gravitational attraction. So this universe is gravitationally unstable. So then from the Einstein point of view, Einstein also was thinking about static universe, that is universe which will not change. So in 1917, Einstein put forward the first futuristic cosmological model, and it was presented before the Hubble discovery of expanding universe in 1929. So he was unaware of this expanding universe, and at that time people usually think that the universe is static. So in order to achieve a static universe, then Einstein has to put something to counterbalance the attractive force, and that was this cosmological constant, which I have shown in here. This cosmological constant. So he had introduced this term to just because it gives you some kind of repulsive effect. And you can always add this cosmological constant lambda, because in technical terms, covariant derivative of this Einstein tensor is 0, covariant derivative of energy momentum tensor is 0, covariant derivative of energy momentum tensor means energy momentum conservation in terms of space time. So, and the covariant derivative of G mu is also 0. You can always add this term in Einstein field equation. So, but usually it is regarded as a blunder of Einstein when he was informed that the universe is expanding through Hubble expansion. But actually, the Einstein's real blunder was not to add this cosmological constant, but to check his equations. But do his equations saying to him? So Einstein's real blunder is not to check whether his solution was stable. So effectively, his solution corresponds to a potential like a helium, and he was trying to balance gravity with repulsive force by putting the universe at the top. So it's a very unstable minimum, unstable equilibrium. So you can see, I mean, so this is a very unstable equilibrium. So you cannot have a static universe. So kinetic energy due to this escape velocity should balance the gravitational pull G m small m over r, and from there you can calculate the escape velocity. And it turns out the escape velocity is proportional to r. So now you can see this Hubble law is also telling you that the velocity of these receding galaxies are proportional to r. So this way you can get an expanding universe which will correspond to a slower rate of collapse. But I mean, how it is expanding in a static universe model? I mean, you cannot have this expanding space too. This is so after World War, they were given these nuclear rates which were used in making nuclear bombs to Gamo, and then they studied this and then they applied this in the very early universe, how these nuclei are formed. And then they have this paper, the origin of chemical elements, the famous alpha, beta, gamma paper. After that, the fine calculation were done in 1967 by Wagner, Fowler and Coyle, and in this way you can calculate the abundance, the concentration of light nuclei, hydrogen, helium, lithium, etc. And all these concentration you can write down in terms of single parameter, which is this eta baryon to photon ratio. And this is now measured by the WMAP experiment, and now we can see the concentration of various elements, and it matches with the experiment. But this thing from here you can reduce by the 5% ordinary matter. So what is the problem? Open question 1, cosmological lithium problem. The Big Bang theory overpredicts. For lithium, it overpredicts the Meyer primordial abundance of lithium is by factor of 2, 3. So this you can see this yellow box and this experiment, and this green box is theoretical prediction as a function of eta, and here you have this CMP data. The CMP data is saying that according to CMP the value should be here, but actually observed value is here, so 2 or 3 factors below. Others are consistent. Other prediction are consistent. So there are many ways people think they can remove this anomaly, but there are few solutions which may require the exotic new physics beyond the standard model of either particle physics or cosmology. Various problems which are you can call it initial condition problem for Big Bang cosmology, and our important challenge is find a standard model of inflation cosmology. And there are various open questions which offer the chance to be at the cutting edge discovery and explore new frontiers beyond the established paradigms. So if there are established paradigms, and you can challenge those standard paradigms and see beyond that. So thank you.
Thank you very much.
Gravitational wave.
luminosity is not the most ideal thing of finding new heavy objects in collisions. In fact, you would like to have more energy, and this is not what we are having. So the risks of finding, or the chances of finding something, are maybe not illustrious to look at these cases. But maybe we have to ask ourselves the question, we have this enormous, powerful accelerator now. Maybe we should also look into make sure that we don't miss anything and look in some other directions. Because maybe we are not looking right at the right place. For example, if the new physics comes dominantly through long-lived particles, then the classical searches would possibly miss that. And as we are at it, obviously, since we have this beautiful machine, we should certainly leave no stone unturned in this last high luminosity run, which we'll have of 10 years, that we don't think in 20 years from now, we should have done this or that, based on the knowledge that we have. So that defined the program which I'm promoting since quite some time, almost 10 years now, and which has developed in a certain way, as you will see, which is searching for long-lived particles. So particles which have long lifetimes on the scale of the detector which we have. And that can arise from hierarchy of scales or small couplings. Then one of the more prominent cases to look at for a long-lived particle in the standard model is the pion. The pion lives long because, in fact, it has three elements that beat it and that make it live long. Now, this is the case of the pion, as you see it, for example, the particle content, the unity bar, for pi plus, and via virtual W, it can decay to a muon and a neutrino, which is actually its dominant decay what it has. And you'll find three elements in there which make it live long. Namely, the couplings at here, these are weak couplings at the vertices with the W here. They are very small. That's one thing. The other thing is that the mediator going in here is incredibly heavy, a W mass, 80 GeV. And the final state which you go into, this new here, is not far away from the total mass of the muon you have. It's only about 50 MeV or something like that. So it's a compressed spectra, heavy mediator, small coupling. This makes that the lifetime of this particle is of the order of 7.8 meter in C.0, which means that when it's boosted with a gamma factor of 20 or so, then it is more than 100 meters on the half-lifetime of that particle. Now, such situations come into new physics as well, even without specially asking for it. You have, for example, our parity-violating supersymmetry, where you have this vertex, for example, going from the supersymmetric particles to the standard model particles, which has a coupling here which can be very, very small. Small coupling can give to long-lived particles. You have others where, for example, you have a decay in this particularly AMSB type SUSY model where you have a charged GNO and it decays into a charged particle plus a neutralino, with the charge here. But the mass degeneracy between these two is very small. It's of the order of the pion mass, so 100, 200 or something MeV. And what then typically happens is you have a particle emitted. This pion will be just having enough Q value here of the decay that you can produce a pion, but with almost no kinematics. So this is largely exaggerated. In fact, this pion will just curl up here at the side. And that also is along with particles. And two more, I won't go explicitly explaining that, but for example, split supersymmetry, when the quarks are very, very heavy in the multi-TeV scale, but the GeNOs are still kind of at hundreds of GeV to TeV scale, and in gauge mediation, you can get these kind of couplings or through to the heavy masses that are involved that you get long-lived particles. So they are sort of naturally coming in many of the models. I gave only a few SUSY examples, you can find more. This is where, for example, small couplings appear in our parity-violating SUSY. In the case of heavy particles, you can have heavy neutrinos. limited phase space compressed through the spectrum. And for example, these are scenarios which give you long-lived particles, and therefore you would want to go out and see if you can detect them. Now, experimentally let's see where we get with that. For example, this is a detector. This is a detector which you have here with the prompt interactions, the tracker, the calorimeter, the muon system outside. And take, for example, a decay, which is like a CT0 value of 5 centimeter, a boost factor of about 30 or so. So this means if it's a 10 GeV particle you're talking about, this new long-lived particle, then this would be 300 GeV. Typically, it has in momentum, corresponds to, by the way, a lifetime of 200 picoseconds. Then you see the fraction that would be detected either as prompt, which is still possible because it's an exponential decay, because it's in lifetime, that it is a very small fraction. 25% would go and decay in the tracker, 60% would decay in the calorimeters, and 30% in the muon system. I must say, this distance here is big for an atlas experiment. It would be a bit more compressed than CMS. And one you wouldn't see at all. But for these, for example, you need to know to make special searches, because that's not part of our standard searches. Take that the CT is 10 times longer, then you see how it changes. It is maybe 1 in 1,000 that you could see as a prompt, 3% in the tracker, and so forth, and even half of them will go outside the detector. And we have no idea at the moment what the CT would be of such a long-lived particle for the scenario that nature may have chosen. You see all around here. Now, the challenges for the experiment are you have to have triggers for that, which you have to usually specially design for that, or piggyback on the CBT triggers or so. That also sometimes work. The standard model backgrounds, meaning stuff coming from the interaction region, is usually low. But you have other things to worry about, like detector effects, punch-through, secondary interactions, tails, cosmics, and so forth, which can create such a topology just by accident. Special reconstruction obviously is often needed, because you see here, you find that guy. Well, we don't have that in our standard reconstruction to find, for example, displaced vertex in here. But we've been developing that over the years. As we got more and more aware, we should do that. And in fact, the upgrades already take into account elements that can help us to identify this, like timing, which is going to be a very important thing here. This we may skip. So, these are some examples which we have done over the years, from the early years, on from basically 2016 or so, looking for displaced for jets, and then you see them being plotted as function of possibly cross-section times branching ratio into this displaced jet, and as a function of the lifetime, CT. And you see there is some optimum space where we have good sensitivity, where they are clearly visible in detectors, and here at the edges it gets more difficult, or the acceptance gets more. Displaced leptons, same as displaced jets, disappearing tracks. I will show an example of that later. We even have looked at stopped particles, which are actually going to the detector, stop there, wait a week or 2 weeks or 3 weeks before they splash in the sense of energy, typically during a time we have no beam in the machine, so we know it's not from the collisions, and look for signatures there, but not found yet. Sometimes one has to be a bit ingenious, so it is also for students, for example, and then for postdocs, a good field to show ingenuity. For example, this is a Gluino type of process, which would be long-lived, and that in some EMSB type of scenario would go then in the decay of a jet and a graphitino, for example. Now, what happens is that if this is being produced and then you see this jet coming out of an angle, that typically the timing will be not the same as you would have a jet coming from the primary vertex. And that is, for example, used cleverly here by using the timing in the calorimeter from the eCal, which has a precision of 200 picoseconds. And here you can see where you can put a cut and say possible dragons or new physics are there, and the standard physics is here. It's a very big logarithmic scale, and you may have some backgrounds in there, but this new physics of the GNSB model would have this kind of acceptance. So you see you have a good acceptance for the model and cut most of the background. Well, no event seen, but limits up to 2.5 TeV set on this long-lived Gloino here, for example. And that's also an interesting one for seeing photons, for example, which come in delay. This type of scenario which we have here, again in GNSB, is this type of scenario where this neutralino is long-lived, and this moves here, for example, and then it will decay into a gravitino as well, and a photon. So a normal photon would work this way. A gravitino with gamma decay could work, for example, this way. So again, you see there is a different path. This is joined there. So not only this is also used as a shower shape, more different from what we have here, but the timing compared to a direct hit from a photon is going to be very different. And like that, you can also get at the moment exclusions, because we haven't seen such event yet. So in the lifetime of this neutralino and the mass which you have here. That's disappearing track kind of case, which we discussed before. So again, I should say that this pion here is largely exaggerated. It's an MSB type of scenario. So you have a chargino going to a neutralino, and they are almost degenerate in mass, except for some energy here which can escape and take away the charge. And so you look actually for a track that just stops and doesn't continue in the detector, and that leaves, for example, this kind of exclusion. And particularly going to lower PTs and lower masses and so on. There are a few plots in there that have been stressed because of time. But let me say something on the metal experiment, because I was a member of that for a long time. This is a small experiment. In fact, this is the experiment you see. This is LHCb, probably not to scale, but this is the metal experiment. And you see it's only 70 physicists, 30 institutes, 14 countries, and it's a passive detector. But a special experiment made to discover new physics, not the classical things, for example, we do in CMS otherwise. What does it look for? It looks for magnetic monopoles, and in fact, MON stands for monopole and exotic detector at the LHC. Now, if you want to have one takeaway message from this talk here, then it's how to pronounce this, because people just don't manage to pronounce it properly. It's metal, it's not model or model or something like that, it's metal, the O is not pronounced. Anyway, so that's what it is, and it looks for example, magnetic monopoles. Now, you know, if you have a normal magnet, that's a north and a south pole, you break it, what you get, not a north and a south pole, but two new magnets with a north and a south pole. That's how it is. But here, it actually looks for something which is either a north or a south pole, which is both a monopole or an anti-monopole. So, and to look for where that exists. Are there any reasons to believe that that exists? Well, you know, Dirac was already one of the people that said that these monopoles should exist, and even calculated what their charge should be in equivalent with electric charge. And in fact, people like Wolf and others believe they exist, in particular in grand unified theories, if of course the nature is being formed like that. But anyway, there are reasons to believe that we should look for that. And what it is that this thing is in fact having a charge which is equivalent to an electric charge, which is much, much higher, almost a factor 50 higher. And that is the signature to look for such a guy. For example, in this experiment, what they put is they put plastic around here, and a monopole, when formed in, for example, the Rayleigh line processes, this one, would actually move through the plastic and drill holes in that. And so you would have to do, you hang your plastic, you go away, you come back at the end of the run with no electronics here, and then you scan the plastic under microscopes and see the 3 consecutive layers You have something like a track there. That's what it would do. Here's some more detail about that, why it would be interesting to have these monopoles. It would make life for students very easy because the Maxwell equations would get symmetrized. Here's some of the explanation and then why monopoles could actually exist, and that's about the charge that has 16.5 times the charge of an electron, which means that the index it gives is the square of that, the charge square. And it's inevitable that it could be that's charge 1, but the monopole would be charge 2, 3, 4, and so forth. That's said. This is the detector setup. It's a passive detector. We do two things. We have plastic in the boxes to see holes. Later, or we try to trap them in aluminum bars, which you put there, which have a very high nuclear spin value, which can glue the monopole onto it and keep it. And we treat that in a special way. As we see here, we have here this hut, which is in the mountains around Zurich, which is the laboratory for natural magnetism from the geophysicists. They have a squid here, a special magnetic magnetometer. This must be away from everything that could affect this on any magnetic or electric fields. And then we put these bars through that device and try to see when it goes through, if it jumps, that will give the idea that there is a monopole in there. So far not. We have put a lot of kilograms of aluminum to through that, but we have not seen a monopole yet. And
P plus is both if we are taking the N as a substrate, and this is with a very low concentration of the petroleum. So when we, without on the P side is 0.02 micron, and on the N side is 23 micron, and if we apply the reverse bias, so what happens, the junction will increase, and it will go to the 0.4 micron to the P side, and the 363 micron, let's say, to the N side. So because of the imbalance in doping densities, the width of the depletion zone is greatest in the likely dope, but means the P junction will expand towards the low likely dope side. So in this example, so the N side, which is the likely dope bulk, becomes the substrate for the particle sensor. And we can use the reverse the scenario for this. We use the T as a substrate and to be used as an implant to use the emission as a particle detector. So as the and then some of the particles produced, let's say the quarks and gluons are produced, and then they travel to short distance, and then they decay. So this is the secondary vertex. So secondary vertex indicates that the annihilation or the creation of particles has happened. So another application of this detector is the reconstruction of the curvature of the tracks in the magnetic field. So we all know that the charged particle bends in the magnetic field. If we apply a magnetic field in the trajectory of these particles, they will bend. And by taking the points, let's say this is a concentric ring of the semiconductor detectors. Also, the particle is going through here, so this will give one space-time point. This will give another space-time time, and then we will connect to see that where the particle is, from where the particle is coming. So this is the primary, the Hall interaction, the primary vertices, and this is the displaced vertices. So if we can measure this gap between the primary and secondary vertices, we can measure the particle lifetime. So because it shows that the particle decays at this point, and by using the magnetic field, we can infer the momentum of the particles. by using the Lorentz force. And the sign of the curvature of either the positive or the negative, we can also determine the sign of the particle, the charge on the particle. So the very first detector was made in 1970s, which had only 20 states. And this has a size of 2.3 centimeters in diameter, and we can compare that our negative point is 2.5 centimeters in diameter. So this we can see the size of this silicon strip detectors. And then in 1982, 56 channel silicon strip detector was made, and that is 10 centimeters. So in the particle physics, these are basically used, the particle physics, we started research for the detectors for very short-lived particles, because heavy parts which travel few millimeters before decay. And then we will, let's say, the deep part, it hadronized basically, and then we can on that and produce the jets, and then if we can able to resolve those jets, we need very precise position resolution detectors. So they basically travel few millimeters from the point of production to the point of decay. So the LHC basically has designed the industry of 10⁻34 parts second per square centimeter, which is the number of infections. And this is happening in a large, this is basically different range. The PS, the SPS, and the LHC is the big one, which is shown there. This is the injection chain, and there are few detectors, CMS, LS, LPS, and LSCP, and we are here working for the CMS. And these are some parameters for the accelerator. 7 tera-electron volt proton using one side, and 7 tera-electron volt proton using on the other side, and they are valued at different inflection points where various gigantic detectors are installed to record the collision particles produced after signal of these programs. So this basically the same as the detector, and this is the size you can imagine with this size of the man. And this is basically the thin pipe, because one proton is coming from this side, another is from this side, and that side is exactly at the center of this cylinder, like detector, whose weight is 14,000 tons, and diameter is 15 meters, and overall length is 29 meters approximately. Then the next side is 3.8 meters. So the silicon tracker where the silicon modules are used are very close to the lead pipe, because they have a high position resolution, and we basically are using the high position resolution detectors here to the lead pipe. So we can record the production points or the secondary vertices if we have high resolution position detectors installed there. So now the upgrade plan of the LHC is that its mechanism in Austria will be increased to 5 times of the 10⁻34 injections per second per square centimeter. This will increase the relative luminosity of this inverse control configuration, inverse control bond energy. So the pile of events will also go up because the number of infections are increasing. So the simultaneous collisions also increase from this. You can see. So this picture is basically showing the pile of events, and but we cannot, resolve this unless we have a very good detector with very high resolution. So this can be done only if we have very good detectors and with a very fast that can collect information in a very fast manner. So what happens the level 1 filter, so here we are here basically now, and this is the same as base upgrade. So when we are increasing the luminosity of the LHC, means the number of impressions per second is increasing in the LHC, so it will So it will produce more particles. So more particles, so the existing CMS experiment or other experiments which are using different types of detectors cannot record those interactions and could be confused. So in order to get the data properly, we need to upgrade the experiments with the upgraded technology of detectors that should not be compromised for this highly university upgrade. And this is basically we are increasing to find the rare processes of physics which have very low cross sections. To produce those events, we need to increase the luminosity of the LHC. Or in other words, you can say the statistics of the events can be increased by increasing the luminosity. So this is basically this is how the detectors are oriented or placed in the CMS experiment. So this the x-axis is showing the beam is along the beam pipe, and this line shows the vertical to the beam. This axis shows what is vertical to the beam. So this the region is basically the inflection point, and this is basically the one quadrant of one CMS experiment, and this is how they are categorized into different detectors. There are different kinds of detectors installed. For the very inside, very close to the beam pipe, there is inner tracker, and after 200 millimeters there to I think 1200 millimeters. This is the outer tracker. So outer tracker part. So this line, this short line, is basically showing the detectors. Okay. And they are named like this. Is the DB2S because this outer tracker has two types of detectors. One is the strip detector, and other is the pixel strip detector. So this outer tracker part, the strip detector or the 2S module, which we say is something like this, and the 2S module is one here. So both are basically they have two strip sensors, and they are separated by 1.8 or 4 millimeter spacing, two back-to-back sensors, and sensor size is 10 to 10 centimeters. Or it has strips around 1016 on one side and 1016 on this side on one sensor, and they are of the length 5 centimeter and the length 2 micrometer each. And for the PS, this is a pixel and the strip sensors are combined together, and they are having with 3 elements with different manifestations. The sensor size is basically the strip size is a half of this US module, and the macropixel size is basically around 100 micron, 1.5 millimeter, very small. So by doing this, as we discussed earlier, that because these are basically strips and pixels are basically the readouts of the chart that is coming from the incident particles. So if we can reduce more and more the size of these readouts, so what we are getting more and more high resolution. So we can precisely say that the particle is coming from this point, or if we have larger size readout, then we can say that okay, this much that is 2.5 centimeter. We can say that the resolution is limited to this number. So this is how the things are in the CMS experiment. And the inner tracker here is a pixel.
मिस वाले और कोई भी नहीं है ना हमारी क्लास से?
नहीं, PhD वाले।
चलते चलते लेते हैं ना।
Assalamualaikum. So today we are at NCP 13 Summer School. So सजाद भाई हमारे साथ हैं, कैसा एक्सपीरियंस है आपका?
यार बहुत ही अच्छा एक्सपीरियंस है यार, यहाँ पे बहुत कुछ हम लर्न कर रहे हैं, तो देखते हैं लेट्स सी क्या होता है।
एग्जैक्टली दिस हमारा फर्स्ट समर स्कूल है LHC Physics, देखते हैं इंशाल्लाह काफ़ी कुछ सीखने को मिल रहा है। तो अभी हमारे सेशन चल रहे हैं, अभी जस्ट हमने लंच किया है, सो जस्ट घूमने